Hello, I'm Mr. McBrien. This is SPH3U, Projectile Motion Problem Solving. Today we're going to consider the problem of projectile motion and predicting the position, the velocity, or the range of a projectile. Previously we talked about the equations that define projectile motion in the x and y domain. Today we're going to dig deeper into this and talk about the horizontal or constant motion case and the vertical accelerated case of motion. And we're going to deal with those separately and then use the commonalities between them to arrive at the correct answer for a single problem. Okay, so the first step then in defining the motion of a projectile is to break up its movement into the x and y domain. And most commonly, we'll be looking at the v1, the initial velocity for a projectile, and then considering the v2 case. So we need to break up v1 into v1x and v1y. And we've seen how to do this before. So here's a standard problem. An object is launched at 15 meters per second, 37 degrees above the horizontal. And our challenge is to break up this v1 vector into a v1x and a v1y vector. And we've already seen how to do this. So we can use trigonometry to use the angle and the hypotenuse magnitude. And in this case, to get the horizontal velocity, cos 37 degrees equals x over 15 meters per second. Rearrange the equation to get x equals 15 meters per second times cos 37 degrees, or x equals 12 meters per second. Similarly, we can treat the y case. So sine 37 degrees equals y over 15 meters per second. Y equals 15 meters per second times sine 37 degrees, or y equals 9 meters per second. So in a few seconds we have extracted the individual components for the motion, and now we can use those to go further if desired. So one of the problems with which we might be faced is the problem of getting the velocity final from the velocity initial. And this simple case of a cannon firing a projectile in the x direction 20 meters per second, and knowing that its altitude is a given value, we can ask what is the final velocity represented here. And in this case, it's essentially a trivial exercise to go through and find v2y from v1y plus acceleration times the hang time. And this is a pretty standard equation that we're going to use over and over again. Once we've found that v2y, v2 overall is just the resultant of the two components, vx and vy. And of course, vx is the same as it was at the start, since we don't have acceleration in the x direction. So vx2 is equal to vx1 in virtually every case, and all we're doing is adding the new v2y vector to that v2x vector to get our final overall velocity. And of course we do this as seen yesterday, as seen last lecture, using the Pythagorean theorem to get the intensity, and using tangent for the relative intensities to get the angle. Now, if we were asked for the displacement, so obviously the displacement in the x and y direction, then that's a different problem. Essentially, we need to define the displacement in the x direction, the displacement in the y direction, and then combine these together. And this is represented pretty well in this graphic here. So our displacement in the x direction is represented in green, in the y direction is represented in blue, and overall is in red. And obviously the equations for these two things are very different. But what they have in common is the hang time, delta t. Most often that will be the hang time, but we can, if we want to be more general, we can talk about the duration of the experiment. In many cases, we will find that projectile motion problems require us to solve for delta t, and we'll see how to do that right now. So in this example, the projectile is launched at 15 meters per second, 37 degrees above the horizontal. What's the maximum height above its launch position from ground level? Okay, this is a relatively simple problem. First off, we need to consider that at maximum height, v2y is going to equal 0. So, if we perform the Gus exercise, we get v1y equals 9 meters per second, v2y equals 0, and the acceleration is negative 9.8 meters per second squared. And the question becomes, what's delta t? So it's pretty easy to get this. We simply have to use our equation for constant acceleration, rearrange it to get delta t equals v2y minus v1y over a. Substitute in, and we find that the duration of the experiment to get to maximum height is 0.918 seconds. Obviously, for significant figures, if this were our final answer, we would be reporting 2 significant figures. We can carry one more since we're going to use this information further. Okay, so now we can consider further the problem of displacement. How high does the projectile go? So we can substitute in, for our case for displacement, substitute in v1y, our time of the experiment, and 1/2 negative 9.8 meters per second squared, again times the time of the experiment squared. And we find that the projectile goes up 4.1 meters before it stops rising. So if that were the question, how high does it go? At the top of its arc, we'd have an answer. But if the question were rather, how far does the projectile travel horizontally before it lands? In other words, what's the range? Then our question isn't done. Now it's important that we keep in mind that to this point we have only calculated the time that the projectile took to go up to the apex. And of course we've seen many times before that due to symmetry, the time coming back down is going to be the same. So we double it, and this gives us the hang time for the projectile. 2 times 0.918 seconds equals 1.836 seconds. And then we can substitute into the constant speed equation in the x domain to find out how far the projectile travels in the x direction, and it's simply v1x times delta t, 12 meters per second times 1.836 seconds equals 22 meters. So the range of our projectile is 22 meters. Now we could have, if we had just simply been asked for the range, we could have solved this in a single step if we wanted to. So we can say that our delta dy equals 0. In other words, our displacement is 0 across the experiment in the y direction. We started at ground level and we finished at ground level. We can say that our acceleration is negative 9.8 meters per second squared again. And we can say that our v1y is again 9.0 meters per second, and simply solve for the time. So what's this look like? Well, we get an expression for time, v1y delta t plus 1/2 a delta t squared equals 0, equals delta d. And you can see that there are two solutions for this problem, right? So there's the problem of delta t equals 0 will give us 0. And this is reasonable because at the beginning of our experiment at time 0, our projectile is at 0 displacement in the y direction. It's at ground level. But we're not interested in that case, so we set delta t is not equal to 0, since that's the trivial half of the answer, and instead solve for the other half of the expression and get delta t equals negative 2 v1y over a. And we can solve for this and get delta t equals 1.837 seconds, which is the same answer we got by using the multi-step approach. So we've seen two ways then to solve that problem. We've got lots of practice problems available in the textbook. Please proceed to move through those questions, and we'll take some of them up tomorrow. Thank you.